Okay, so just a quick summary. What we've been talking about up to this point is that we were talking about capacitors. And remember that the capacitor is a physical instance or it's a device that has to do with or that has a certain capacitance. And when we're talking about devices, these devices can be connected in different ways. They can be connected in series or they can be connected in parallel. Okay. And so depending on how the devices are connected and what type of device we're talking about, there's going to be certain characteristics and properties of that particular array or arrangement. And so what we're seeing here, this was kind of a summary of the series and parallel characteristics, okay, that we were talking about last class, okay. And so in the case of a series connection, the charge is going to be the same, okay. The voltage is going to be distributed uniformly between the elements. The total capacitance is going to be the sum. The reciprocal of the total capacitance is going to be the sum of the reciprocals, okay? Or the inverse of the capacitance is going to be the sum of the inverse of each of the capacitance elements. The total capacitance is going to be smaller than the individual capacitance. In the case of a parallel array or connection, the voltage is always going to be the same in a parallel connection. The charges are going to be distributed. Here it's much simpler. The total capacitance is simply going to be the algebraic sum of each of the individual capacitances. It's always going to be positive. A capacitance is never going to be negative. And the total capacitance is going to be larger than the individual capacitance in the circuit. Okay, so that's kind of a summary of what we were talking about last class. And we saw a couple of examples just with series, and we saw another one just with parallel. What we're going to be doing now is seeing some examples that combine both series and parallel connections. Okay. These examples, we're going to be doing 4 exercises. Or we're going to be doing 6 exercises. We're going to start off with these 4. And in these exercises, we have an array of many capacitors. And what we want to find is we want to find the total capacitance. For these exercises, we're just interested in the total capacitance. These capacitors don't have a voltage supply connected to it or anything like that. We just want to find the total capacitance. Now, these exercises can be a little bit tricky because we need to visualize. We only have 2 types of connections, you guys. 2 types of, it's either series or parallel. Okay? And that's important. There's only 2 types of connections, series or parallel. If it's not series or parallel, clearly, it means I have to do some sort of manipulation or reduction in the circuit. The way we approach these problems is that we need to identify in the circuit, we need to identify what connections are clearly series and what connections are clearly parallel, and focus on those. And so that's I'm going to give you tips. So the first one is that identify connections that are clearly series or clearly parallel. Try to look at pairs. Pairs of these 2 capacitors are in series, so I can reduce them. These 2 capacitors are in parallel. And we're going to do the reduction of the circuit to get the total capacitance step by step. And we're usually going to be working or doing things in pairs. Okay, so let's let's start with the first one. Oh, and by the way, when you guys do the exercises, maybe in a homework task or an exam, please try to follow a procedure like the ones I'm going to try to be doing during class, where we go step by step. Okay. Why is that? Because if we go step by step, then I can check where maybe if the total result is wrong, well, maybe I can check where you guys did a mistake, and maybe up to that point, the rest is okay. And actually, that's the way I graded the exams. So some of you, for example, had errors in calculations of distances that had to do with trigonometry. So that deducted points. But if the overall analysis was correct, then I only deducted points for the calculation, not for the whole problem. I actually only either deducted a lot of points or put the problem wrong, where definitely the analysis of the problem was completely wrong. Okay. But if you did a calculation of a distance wrong, then that deducted 2 points. If that gave you that the sum of forces in X or Y was wrong, then that deducted 2 points as well, but the whole problem was wrong. So that's what I want us to think about here. So I'm gonna be writing here on the tablet. I'm gonna be here in the desk, but I think I can see you guys, so we're good. And the microphone is going to be able to catch what I'm saying better here. So first off, I'm going to be asking some very basic questions. Very basic questions. How many capacitors do we have in that array? I'm actually going to number them just so we have. I'm going to say this one is C1. I'm going to say this one is C2. And I'm going to say this one is C3. So we've got 3 capacitors. Okay. Looking at that circuit and looking at capacitors in pairs. That's a tip that I'm going to give you. Looking at them in pairs. Are there any 2 capacitors there that are clearly connected in series or clearly connected in parallel? Yes, which ones?
1 and 2, they are in
1 and 2, okay. So capacitors 1 and 2 are clearly connected in series. So these 2 are in series. Now it's being recorded as well, but pay attention because I'm going to be giving you some pointers and some tips for when you analyze more complex situations. Those are clearly in series. Now, how do I know they're clearly in series? Remember that series means that there's a chain. It goes from one point to the other, and there's nothing interrupting the 2 elements. It's like a chain. Okay. Remember when you guys were holding hands or holding the Oreos? It's a chain. So if I go from capacitor 1 to capacitor 2, there's a path going there, and there's nothing interrupting that. That's why it's in series. Okay. That's clear? Now, capacitors 1 and 3 are not in series. Why can somebody tell me why these 2 are not in series? They're not parallel. There's a branch. There's something here in the middle. If this wasn't here, then they would be in series. But there's something in the middle that's interrupting the connection. So they're not in series. Now, Enya, you said parallel. You have to be very careful with something. That's why I mentioned at the beginning. Either they are clearly in series or they are clearly in parallel. But if they are not in series, it doesn't mean they're in parallel. And if they're not in parallel, it doesn't mean they're in series by default. So first off, it's clear that these 2 are in series, right? Okay. Now, why are they not in parallel? Well, for a parallel connection, Remember that we've got two arms. Each of the components has two sides. The two sides have to be connected to the corresponding to the other element. So one leg or one side of capacitor 3 is connected to capacitor 1. Can you see that? But is the other side of capacitor 3 connected to the other side of capacitor 1? So they're not in parallel. You see that? I'm going to repeat it. One side of capacitor 3 is connected to one side of capacitor 1. But the other side of capacitor 3 is not connected to the other side of capacitor 1. So they're not in parallel. Okay? Is that clear? So if they're neither in series nor in parallel, we're not going to mess with them. That means we can't do anything with them right now. Okay? Is that clear? Okay, so what we clearly see is that capacitors 1 and 2 are in series. Okay? So what I'm going to do right now is the following, and I'm going to ask you guys to please help me out with, when I ask you to please help me out with the calculations. We're going to be doing this step by step. If I know that capacitor 1 and 2 are in series, then I can redraw this circuit this way. This is still capacitor 3. And I'm going to call this capacitor capacitor 1 and 2. Okay? What is the value of capacitor 1 and 2? Well, let's calculate that. They are in series, so that means that 1 divided by capacitor 1 and 2 is equal to, or rather, capacitor 1, 2 is going to be equal to 1 divided by capacitor 1 plus 1 divided by capacitor 2, and all of that is going to be elevated to the -1. This is going to be equal to 1 divided by, remember that the mu is micro, that's times 10 to the -6. So this is going to be 10 times 10 to the -6 plus 1 divided by 0.3 times 10 to the -6.
Why is it to the -1?
Excuse me? Yes, Vivian?
Why is it to the -1?
Oh, capacitors in series, it's 1 divided by the total capacitance is equal to 1 divided by capacitor 1, 1 divided by capacitor 2. So instead of writing 1 divided by the total capacitance, it's the same as saying that all of this is to the -1. Okay. Or the other thing, Viviana, is that you could just calculate all of this, and then you would have you divide 1 divided by that, and that's the total capacity. It's equivalent. Okay, and so we're going to get a value here. And can somebody calculate that value, and let's corroborate, please?
The second parenthesis.
Yep, we're missing the -1 thinking. -1. There we go. Did you get the value, please? Calculate the value, and everybody try to calculate the value, and let's corroborate. If somebody has it already, then let me know. Mhm. You got 2.91 times 10 to the -7. You got something different, Lisa? So could we please corroborate that?
have the same, but.
I got 2.91 times 10 to the minus. No?
Yes, it's to the minus 7.
To the -7, let me just check.
That's minus, yeah.
To the -7?
Yes, I got to the minus 7.
So 2.91 to the times 10 to the -7. We got that value? Okay. Okay, so that is the capacitor 1 and 2. Okay. Now, these two capacitors that I have from making the first reduction, are these, can we say that they are clearly in series or clearly in parallel?
Yes.
What, yes to what? That was a very diplomatic answer. Is it one or is it two?
They are
Yes.
parallel.
That's the way Sarah answers things. So Sarah, when she's watching the TV, she's really very focused on the TV. So Sarah, do you want Fruit Loops or Cocoa Puffs?
Yeah.
She's like, yes. Okay, Sarah, do you want $1 million? Yes. And I have to literally turn her head so she can see me and answer. So I'm gonna ask you again, is it clearly in series or in parallel? In parallel. Now, how do we know it's clearly in parallel? Because again, the two capacitors are connected on both sides. So this is a parallel. The two sides of each capacitor are connected together. It's not series because the connection is interrupted by the two cables in the middle, so it's parallel. So this is going to give me one capacitor that's going to be C123, which is actually the total capacitance because that's the last capacitor I have from doing the reduction. And this C123, if they're in parallel, then what would be the calculation we would do?
It's elevated to make one, right?
Which one?
The last part.
Uh-huh.
Because it still doesn't.
You're just going to add.
It gives you a different result? What, it gives you a different result?
It gives me the same result, but like to the, not to the minus, to the plus.
To the +7?
Yes, because
We need,
before I do the minus one, the elevator to
-1?
it gives me like 0.000000043, and then I do it, and it gives me.
Just check, double check. Lisa, when you're doing the 1 divided, that you are putting the minus here in the bottom, because this, because what Lisa is asking, just remember you guys, debugging is important. Whenever we get a result that isn't correct, we need to kind of find out where it is. So 1 divided by something very small plus 1 divided by something very small. This number here should be a large number, not a small number. And then elevated to the -1, that's why we should get. So whenever we're doing calculations of capacitance or charge, we should be in the range of micros or nanos. We should be to the -7, -6, -9. Those are normal values. So just to double check that, and we can actually check that in a moment. If the capacitors are in parallel, how do we do the calculation? We just add the two capacitors. So in this case, C123 is going to be the capacitance of 1, 2 plus the capacitance of 3. And so this is going to be 2.91 times 10 to the -7 farads plus 2.5 to the -6. And so the total capacitance
Like 79.
2.79
2.79 times 10 to the minus 6.
farads, and this would be 2.79 microfarads. And that would be our total capacitance, or our equivalent capacitance. Okay, so just verify those. Yes. Remember, we're going long, and if you need to step out, just let me know.
Professor,
Yes.
can you write down those formulas for Earl? If I wasn't, if that-
Sure. I'm gonna put them here, and I'm gonna erase them in a moment. So for series, and Diego, I'm gonna put the general notation, because right now we're seeing 2, but we could have 3, 4, 5, or 6 connected in the same. So for series, the total capacitance of a series array is gonna be the sum of the inverse elevated to the -1. Okay. So what does this mean? For example, Diego, if I have 2 capacitors, it's going to be 1 divided by C1 plus 1 divided by C2 elevated to the -1. Okay. And in parallel, the total capacitance is simply going to be the sum of the capacitance. So when it's in parallel, if you have 2 capacitors, it's just going to be 1 plus the other. Okay. For the charge and the voltage, no, for the charge and the voltage, let's just remember the previous slide, which was the summary. Can I erase this?
Yes.
Yeah, okay. So in the case of series, if you had n amount of capacitors, all the capacitors are going to have the same charge, and the voltage is going to be distributed. In parallel, the voltage is the same and the charge is distributed. And the relationship between the charge and the voltage is that the charge is equal to the capacitance times the voltage. And that also gives you that the voltage is equal to the charge divided by the capacitance. And it also gives you that the capacitance is charge divided by voltage. Okay, so either of those 3 formulas you can use to find the rest.
Yeah, I just want to know if it's gonna be the same for series and parallel.
Mhm.
I just need to know what was the same.
The relationships. Okay. Okay. So that was the first one. Questions with the first one? It was relatively simple. Let's do this one, and I'm going to give you a few minutes to try to do that on your own, and then we'll try to solve it here. I'm going to leave the mic open and keep recording. If questions come up, I'm going to give you a few minutes to try to do that one. No, for these examples, what we're doing is we're practicing the total capacity. I want you to kind of try to first understand the circuits, and then we're going to mix it up and add with our voltage supply and calculate the rest of the things. But right now, we're practicing this. Okay. Let's start, look, no, no, we do not want to solve it. No. Two more. Two. Two more. We'll verify the result in a moment. I have the procedures here, but I don't have the calculations. One more minute, so we don't have.
Syntax error.
Syntax error, wow, that shouldn't happen. Okay, now let's start seeing how we could address it. Wow, this is it's the first time I've had a group that said, no, please do not solve the problem. Do not solve the problem.
Yeah.
And remember the order of the operations, that's also important. Remember the order of the operations and the scientific notation. So it's not the same to say 1 divided by. So it's not the same that I have 2 times 10 to the minus 6 and 1 divided by that, then 1 divided by 2 over 8 times 10 to the minus 6. So when we do the 10 to the minus 6 of the micros, we have to do it with the quantity, not after the mathematical operation. So be careful with that. Okay, so let's start off with the procedure and we'll validate the calculations. So first off, let me name the capacitors. I'm going to say this is C1. This is C2. And this is C3. Are any of these capacitors in pairs either clearly in series or clearly in parallel?
Yes.
Uh-huh. Which ones?
I think
Which ones, Andrea?
C2 and C3 are.
2 and 3. Okay.
Oh, they're series. They first start.
Now they're in parallel.
The numbers are different. Than-
So these two,
No, no, es más, pero ahí tienen los números.
yeah, maybe I named them differently, so just don't mind that. So those two, C2 and C3, are clearly in parallel. Okay? And if they're clearly in parallel, then we're going to have the following array here. No, by the way, technically the answer you guys were giving us correct because I was asking, are any of these capacitors clearly in series or clearly in parallel? The answer to that question is yes. So even if you answered yes, it's not incorrect. You can just answer yes and that's fine. It's not incorrect. Now specifically which ones are in series and parallel, that's another issue. So this is still going to be C1. And this is going to be the combination of C2 and C3. Now, C2 and C3 are in parallel. And so the parallel calculation is simply the sum of those two. It's going to be C2 plus C3. This is going to be 10 times 10 to the minus 6 plus 2.5 times 10 to the minus 6. So C23 is going to be equal to 12.5 times 10.
Backwards, have the same result. Like first we do the series and then the parallel.
Okay, so let's actually no, and that's important. So these two are in parallel. When we combine them, we get this, and these are clearly in series. If you're saying it backwards, well, before I answer, what do you mean exactly when you say backwards? Because maybe it is right. But I don't know.
No, because it's not going to be the same because we added C3 and C2, C1, sorry.
Oh, no, because C1, and that's why I say that C1 is clearly not in series or in parallel with any of these two. It's in series with the combination, which is what we're calculating over here. Okay.
I got that.
It's basically, we're moving this point over here, so this will get. Sometimes the calculator is going to do that automatically, even if it's a very simple calculation, it's going to do that. Okay. Now this combination that we have here, this is clearly in series. And so this is going to give us a total capacitance that's going to be C123. And that capacitance is going to be 1 divided by C1 plus 1 divided by C12 elevated to the -1. This is going to be 1 divided by 0.3 times 10 to the -6 plus C1, C23. I'm sorry. Oh, I wrote that down wrong. Yep. It's C23. Correct. Thank you. Anya. So what value did you get for C123? 2.92 times 10 to the -7 farads, and that's going to be the total capacitance. Which would be equivalent to having 0.29 microfarad. Does that calculation add up? Did you get that same value? Good job.
Think that this model is easier.
I would say yes.
Because I don't know.
With regarding the concepts and calculations and this stuff.
It's more of logic, right?
Yeah, but the thing with learning module 2, because we're going to see these two examples are simple, but I'm going to be giving you some weird arrays. And so you need to visualize some things there. That's the complicated thing about learning module 2. But it's much shorter, I think. I think it's a much more simpler learning module than 1. But and hopefully you guys will do better.
Well, it's very distracting.
Yeah, no, you'll be getting it. Okay, questions with this one? Take a screenshot of this. Okay. Okay, everybody over here. So we're gonna start to add complexity. So let's look at this one. What I want us to do in this one is, I'm gonna give you a couple of minutes. Right now, what I want to do, because we might not get to finish it because there's more than a few calculations. What I want us to understand is the procedure, okay, that we should do in this case. And we're going to be adding complexity. So first thing I'm going to do is that I'm going to put some names to these capacitors. I'm going to say, and let's do the following, at least for this exercise, put the same numbering that I'm going to use here so you can have the same. So I'm going to call this one C1. I'm going to call this one C2, C3, C4, C5, C6. Okay, so this is a more complex array. Now, something that I didn't mention in the previous ones, but it's important to note here in this one. There's always going to be, for these calculations of equivalent or total capacitance, or eventually when we see resistance and inductance, there's always going to be 2 points. And in those 2 points, that in this case are these points that are open here, that's where I'm calculating the equivalent. Or rather, if I were to take a measurement device and put it here, this is where I would measure the equivalent capacitance. So we need to start doing this step by step. And again, I'm going to stress this a lot. Do a step-by-step procedure. If something isn't clearly parallel or clearly series, it means that I need to do something before anything else. Okay, so of this array, the way it is here, is there anything that we need to identify or that we can identify as clearly in series or in parallel of any of the we have there? Any pairs? Which ones and what are they? 1 and 2, and what are 1 and 2? 1 and 2 are parallel. Okay, that's something that we can clearly identify. Let me mark those and let me, if there are, let me answer some questions before we move along. So C1 and C2 are clearly in parallel. Yes.
1, 5, 7, 3, and 6 aren't in series.
1, 5, 7.
Like it's 7.
Oh, you know, no, but you know why they aren't in series? Because there's something here in the middle. So if C2 didn't exist, then yes, 1, 5, and 6. Oh, if C2 and C4 didn't exist, then they would be in series. But they're not in the moment that there's something in the middle. So again, let's do this. Again, I think it's maybe a way. So Viviana, grab your pencil or whatever you're writing with, and give it to Estrella. That's a series connection. Okay. Now, Enya, grab your orange pencil and touch it here in the middle. That turned the connection into something different. It's not series. It's not series because Enya is breaking the connection in the middle. It's not parallel either. So that's a tip. For something to be in series, there has to be a path that isn't interrupted between. So again, if these two weren't here, then yes, 1, 5, and 7 would be in series. But these two interrupt the path. Okay?
So it's like square by square.
So we need to go step by step. So the only thing that we can clearly identify is that 1 and 2 are in parallel. So right now for the procedure I'm going to do, don't worry about the calculations. We're going to do those at the end. I just want us to understand the reduction. Yes, go ahead.
For example, there that you have that in parallel. Can we do another drawing to like drive when they're together? Like,
Yes, that's actually the way I suggest we do things, and that's actually the way I'm going to do it here. So this is the original circuit. The next step is exactly what you're saying, Lisa, and I'm going to be doing it step by step here. So the next step is to say, okay, the first reduction is going to be, these two are going to be joined into one capacitor that I'm going to be calling C12. And I'm going to connect that to the rest of the things that it was connected to. I'm going to put the names at the end. The rest of the things that were already here. So this would be C3. This would be C4, C5, C6, and C7. Okay. Okay, and just I'm going to put some notes here. I'm just going to put some notes here just so we remember, because we're going to do the calculations at the end. This one is parallel. C12 is parallel. That calculation is parallel. Now, from this second version of the circuit, is there anything that I can clearly see that is in series or in parallel?
Yes,
C5 and C3.
Which ones?
C5, C12, and C3.
This is kind of like what you were visualizing this for you. Correct, Javier. These three, there's a closed path between these three. So the three of them are in series. Not with C4 because there's a branch here in C4. But these three are in series. Now, we talked about that we can work in pairs. Or if we clearly identify that more than two are in series or in parallel, we can group them as well. It's not. Yes.
First, we need to calculate C1, C2, and then add them.
And then we add them. Then we calculate those three. So these three, we can clearly identify that are in series, these three. And that gives us another circuit where I'm going to have this one here is going to be, I'm going to call this C 1, 2, 3, 5. This is still C4. This is still C6. And this is still C7. And just as a note, this one here is coming from a series calculation. Okay. Now, of this new circuit, is there anything clearly in series or in parallel? Parallel? Which ones?
3, 1, 2, 3, 5, and 6.
Correct. These two are in parallel. And we're going to redraw this. Correct. This is going to be now C1, 2, 3, 5, 4. I'm putting the order on purpose. So I'm not writing 1, 2, 3, 4, 5. I'm writing 1, 2, 3, 5, 4 on purpose because that's the way we're grouping them. C6 and C7. This one here, just as a note, this one comes from a parallel connection. And the last one, all of these three are in series. And that's going to give us one. This is going to give us just one capacitor here, which is going to be C1, 2, 3, 5, 4, 6, 7, which is actually the total capacitance that we're looking for. And this is coming out of a series connection. Yes.
Is it normal if it's small?
The value? Yeah, yes, actually, remember that when we're talking about whenever we're talking about charges, capacitance, we're talking about small values. So times 10 to the minus 7, times 10 to the minus 9, even times 10 to the minus 12, those are acceptable values. So it can be a very small value.
1 times 10 to the minus 6.
Well, let's do this. So this is the procedure to do the calculations. We need to do the calculations now. So for Friday, do the calculations and we're going to verify them here in class. Okay. I'm going to do a save. I'm going to update the PowerPoint presentation with these screenshots later today, and as well as uploading the YouTube video.